what I wanted to do was actually more aimed towards Piers. Unfortunately, I think he's moved on, but so you'll have to tell him some of the message that I try to.
He'll see the videotape.
Okay, so this whole focus on sort of getting a global view of things really started with this guy Jim Tucker about 1970, in the late 1970s, coming up with the idea of NDVI and applying it to satellite data from the NOAA AVHRR and showing the global changes in phenology of the terrestrial biosphere. At about the same time, Inez Feng, looking at the global network of CO2 measurements that were being conducted principally by Dave Keeling. One of the problems of getting old. Showing that there was very strong oscillation of CO2 concentration that showed a very interesting pattern over the globe, and matched very well with with a rather crude model of CO2 uptake and release, coupled with transport in the global atmosphere. Jim and Inez and Charles Keeling put this together to come up with what I think is one of the most iconic plots that and certainly in my view of coming from biochemistry to thinking of global processes, to see a measurement of essentially a driver, NOAA NDVI measurements correlating very well with the CO2 concentrations. So this is, to me, very much like looking at the light going into a CO2 exchange cuvette, or something on that scale, but actually happening at the planetary scale. This is riveting to me, and I think to a whole community. At the same time, Piers was very much involved in trying to put together a global model, a land surface model that could run with within the GCMs, to do a better job, as he outlined, and Forrest, of covering essentially the physical drivers of the climate system over the land surface. All of these interests, which really had a global genesis, were put together in doing Fife and Boreas to use these as experimental systems to flesh out the understanding which was incorporated into the SIB model. It was not clear at that time that SIB would, or these global models would ever actually connect with physiology. But one of the things that kind of brought me into this conversation was the discovery that if we used fairly simple stomatal models in the in SIB, the land surface became dry. It tended to have a feedback process where if it got hot and dry, there was less rainfall, lower soil moisture, no transpiration, lots of sensible heat, gets hot and dry, and it just goes around this loop. and it gets hotter and drier. So stomatal physiology was something that could fit into this. And I'd had a graduate student, Tim Ball, who'd worked on developing a model of to couple photosynthesis models to with stomata to try and come up with a better to a parameterization that we could use principally in studying plants in the field. But we found that if we used this parameterization in the land surface models, they tended to be more stable. They were more stable because this model depended more on less on the VPD, so that they tended less to close as the temperature went up. The driving force to close stomata did not go up exponentially as the vapor pressure deficit goes up. And that actually quieted down the land surface model, and kind of like the encyclopedia salesman, got a foot in the door for doing, for coupling the land surface models and essentially these global scale models to things that we've been doing for some years at physiological scales. This is Graham Farquhar and Susanna von Kammerer, two of the authors of our photosynthesis model. It basically, these are photos of about the time that they did this work in their early 30s. And the idea that drove this was just basically that that photosynthesis is a very complex process with lots and lots of steps, but you could simplify it to who's in charge, and under conditions where light is low, the light reactions are in charge. Where light is high and maybe carbon is limiting, stomata are closed or something like that, the dark reactions are in charge, and it's this teeter-totter. Jim Kolatz who's a graduate student at the time, or actually a graduate student and then a postdoc at the time, not only is a good musician with a guitar, but also with equations, and was able to put this all together into code that could operate within the within SIB. And Chris and Hal Mooney were also involved in this, in essentially coming up with better ways to couple all of this to the biomass, respiratory activities, and the net primary productivity of the biosphere. So this was all put together under an EOS project. Looks like when I switched this to PowerPoint that it put moved my bracket over, but this was an EOS project, actually very much shepherded by Diane. I really appreciate the work she did in running interference for us in this, where we attempted to, put together essentially atmospheric GCM, land surface, remote sensing, plant physiology, some ecology, and carbon cycle to and this was occurring simultaneously with Fife and Boreas. So we're able to incorporate a lot of this information into making this work. It's worked quite well, and as Alan developed, there are a number of insights into how the global system works, which link to this. I think from my own perspective, what I've discovered in this is just how important it is to understand, first of all, what's there. Secondly, to have very good forcing data. You have to have, in order to make a model like a land surface model, the plant physiology and the ecology, you have to have the temperatures, the soil moisture, all of the components that make it work. You also have to have information on the capacities of the elements that you're trying to simulate. If you have all that, it works pretty well. If you don't have that, it can be very much an error. Rather than go in more depth into that, I thought I'd fast forward to the present. This is a graph showing a latitudinal plot of GPP, gross primary productivity. This was put together by the folks at the Max Planck Biogeochemistry Institute, Christian Beer and Marcus Reckstein. They showed that the pink area is now where all of the sort of process models, the kinds of models that we developed with peers, using physiology coupled to models of the climate system. The black line is a model that is based on an statistical analysis of the flux sites, of about 105, 110 flux sites. I think there's something like, there's several thousand years of flux observations gone into this, and what they've done is to take a machine learning approach to fit those data and then apply it on a global scale using the parameters, using the drivers that they've come up with. And what you see is that there's a much larger variation in the modeled output using process models than in the constrained models which fit the data. Two things I think really govern this. The first is that these are free-running models within the context of GCMs, and the forcing data is noisy, and in many cases the errors shown by the very wide red, the colored areas are because precipitation in particular is wrong. The other problem here is that these are free-running models which are designed to simulate the changes in the biosphere in response to climate change, particularly to increases in CO2 concentration and other things which are then important in assessing the carbon-climate feedback in the system. That is an uncoupling of these models from the reality check which we've had with remote sensing. So in some ways, we've taken a step back from what we've learned from Boreas and Fife and started applying the models in a free-running way and have not really focused very much on using remote sensing to drive these. Remote sensing is really critical for all three parts of that, what we need. It's critical for finding out how much is there, how it functions, and for checking the forcing data. One of the things that Piers gets a lot of credit for organizing these things and for generally having general insight. One of the things that I find really most fascinating about him is that he has also approached this from a very quantitative mathematical approach. In the early 80s, he took the general ideas that were floating around on empirical uses of remote sensing and put them into a differential equation format. This is the two-stream approximation for expressing absorption, for expressing essentially light transmission through a diffuse medium, and as a function of things like the transmission and reflection coefficients of the components of the system as a function of wavelength. One of the things that he found is that the absorption of PAR in the system was very closely coupled to the reflection of near-infrared radiation. This was difficult to use because it's hard to separate the reflectance from mixed scenes, but it's quite a powerful observation. His work at the time focused much more on using using ratios, the simple ratio and NDVI, because these were much more easily accessible from the satellite data. But this is something that's always kind of stuck in our mind. Recently, we've been involved very much in looking at chlorophyll fluorescence coming from the land biosphere. It comes from the chloroplasts. One of the really important properties of this system, or of this retrieval, is that it is extremely specific, as opposed to other kinds of remote sensing where anything can reflect light and you can get complex patterns because of that. It's like looking at the night sky, at the night lights coming from the land surface. Only the plants glow. And you can see this is top is an image in RGB, and at the bottom a fluorescence image. The bare fields show nothing, and the plants glow. We do this in the Amazon as well. One of the things that we saw in looking at the Amazon was that the solar-induced fluorescence was very closely coupled to the actual emission, the long wave emissions in adjacent wavelengths. There's huge variations here in driving light intensity, but it quiets down if you look at it in terms of the reflected near-infrared radiation. When we looked at reflected radiation, NIR totaled coming from systems in comparison to the SIF that's observed, we saw that when you have very high NDVIs and very high vegetation closure, the system behaves very much like the Amazon. There's a very close correlation between NIR and vegetated fraction. If you go down in look at less vegetated pixels, that correlation disappears. If you multiply the NDVI times the observed NIR radiation coming off, you get a very good correlation. We developed some equations to actually compare the NIR coming off of vegetation in two-stream approximation to that seen, to that we would predict with these either a very crude total NIR times the NDVI or a more complicated equation. They seem to work pretty well. The one on the right seems to be a better predictor. We know that the SIF is related to GPP. If we look at the MPI GPP versus SIF from GOM, we get a pretty good correlation, 0.8. If we look at use MODIS to generate the same pattern, the same NDVI-V, which we think is correlated with SIF, we actually get a much better correlation of around 0.9. That is done at ½ degree. With the MODIS, we can actually go down to 500 meters, so we can then look at flux sites. And if we look at the flux sites, looking at the GPP, sort of monthly GPP over time, what we see is that correlated with NDVI or FPAR, standard MODIS direct products, or the MODIS GPP, we can determine the correlation coefficient for GPP is pretty good. And if we look at the, if we look at that for just the single NIRV, this NIR that we think is associated, is specifically calculating the NIR reflectance that's coming off the vegetation. It's a single product. We're getting as good as a model of GPP. So just to finish that off, I think we've come up with a way to use MODIS that is a bit different. It seems to have a very nice coupling to photosynthesis, and it seems to be a subtle feature of canopy structure. It also includes physiological information, which I haven't put into this, but I'll stop with that and hope we can get a chance to discuss it over the course of this meeting.